Let's see how Tesla's AI understands the road. We talk about self-driving autonomous cars. So how Tesla's AI understands the road. So here we have a combination of computer vision, geometry, and prediction. So, and from camera pixels to autonomous driving. An autonomous vehicle does not directly see the road the way a human does. Instead, it receives numerical information from cameras and other sensors and uses artificial intelligence, mathematics, and geometry, as well as probability and prediction to construct an internal representation of the surrounding environment. So the car is really not seeing like you would expect humans to see. So the central idea of this lesson is you have pixels, from to projected to cameras. Uh, then objects can be visualized, and then geometry, motion, prediction, and actions are taken by the car. So we'll focus on three major mathematical ideas. First, we talk about computer vision, what is in the scene, what is actually ahead of the car. Then you have geometry where everything is in three-dimensional space, and you have prediction, what is likely to happen next. So it is the combination of computer vision, geometry, and prediction that makes autonomous cars possible. So the learning objectives are by the end of this lesson, you should be able to explain how camera images become numerical data, because of course everything is broken down to pixels. Then describe how neural networks extract visual features, distinguish image classification, object detection, and segmentation. Then explain the basic geometry of camera projection, estimate object depth using a simplified camera model, understand perspective and vanishing points, represent lanes mathematically, estimate velocity and acceleration from consecutive observations, use simple physics to predict future positions, understand probabilistic trajectory prediction, explain object tracking and state space models, and understand time to collision. So, of course, because I mean, a car, everything a driver is doing is to avoid obstacles, to avoid colliding with other objects or other cars or whatever. So explain why uncertainty is fundamental to autonomous driving and build small Python simulations illustrating perception, geometry, and prediction. By the way, this is just a sneak peek into the reality. It's not like this is exactly what everything looks like, but this is just telling us the workings of Tesla AI. So the fundamental problem is about turning pixels into decisions. A camera produces an image, of course, that's why autonomous cars, basically, it's all about the cameras all over the place. So a camera produces an image. A human might immediately interpret the image as there's a car 20 meters ahead, a pedestrian near the sidewalk, and the road curves slightly to the left. And then a computer initially sees only numbers. So for an RGB image with height H and width W and three color channels, we can represent the image as I as an element of H by W by 3 real number system. So the autonomous driving problem is therefore fundamentally a transformation problem from image data to scene understanding to prediction and to decision. So that's why when you see an autonomous car, so waiting because that's cited an observation. It's not because it actually saw the thing like a human would see, but it has received numerical signals that helps it to make that decision. So the system has to infer meaningful information from raw numerical measurements. So because computers only understand numbers, in natural language processing, computers don't understand our human languages. But they only understand how human languages, when they are broken down into numbers, then the computers can understand and then take action. So the autonomous driving AI pipeline is this. So we have a simplified conceptual pipeline. You have camera images resulting to computer vision, resulting to 3D geometry, resulting to object tracking, motion estimation, prediction, and if a decision is made. So the decision to reverse, to move forward, to stop, and all of these things. So we can visualize the process as first, we have camera images leading to computer vision. What is the scene? And then it goes to geometry. Where is everything? Where is that tree? Where is the man standing by the roadside and things like that? Then it leads to tracking. How is it moving? Then prediction, what happens next? And then a decision or action is taken. Decision to stop or to continue driving or to turn to the left and things like that based on the information that has been fed into it. So the important insight is that autonomous driving is not simply image classification. It is a combination of perception, geometry, temporal reasoning, probability, and prediction. So images are numerical tensors, straight up. So a digital color image can be represented as a three-dimensional numerical array. So for an image with height h, width w, and channels 3, that's three colors now. We have I as an element of r, h by w by 3. So for a 1920 times 1080 RGB image, the number of pixel channel values is 1920 times 1080 times 3. That's 6,220,800. Thus, a single image already contains millions of numerical values like that. So, for an 8-bit image now, I sub ijk, from here now, I talking about the height, the width, and the color channels is actually lies between 0 and 255. So machine learning systems commonly normalize pixel values as I prime equals 1 over I over 255 to keep it to keep I prime between 0 and 1 like that. So imagine creating an image tensor, import numpy as NP, and you have height 1080, just like what we have up here. Oh, okay, not exactly that. So you have height 1080 with 1920 and three color channels. So the image now can be, height, width, and take the channels, and you can print the image and the image shape and the image size in terms of numbers, by the way. And then the image shape is like 1080 by 1920 and 3. And the number of values is multiplying it all together. So you have 1008 multiplied by 1920 multiplied by 3. And then you get the 6,220,800 values like that. So that's a lot of number to deal with. But the reality is even more than that. So for computer vision, now teaching machines to see. So computer vision is all about teaching machines to see. So and that's why a library like OpenCV is used, when it comes to computer vision. Computer vision, that's in Python. Computer vision attempts to extract meaningful information from images. So a neural network may gradually learn representations corresponding to edges, corners, textures, shapes, object parts, complete objects, spatial relationships. The transformation can be represented conceptually as I going to F1 to F2 to F3 all the way to Fn, where Fi represents learned feature representation. Early layers may respond to simple visual patterns, while deep layers can represent increasingly complex structures. So all this now represents learned feature representation. So different features are learned about the road, the objects, and things like that. So for autonomous driving, the final representation may support recognition of vehicles, pedestrians. These are different features that the representations may be like for an autonomous car. So vehicles, pedestrians, cyclists, traffic lights, road signs, lanes, curbs, road boundaries, and other objects like even like trees and all that. Then we talk about convolution, which is a basic computer vision operation. So one traditional operation used in image processing and convolutional neural networks is convolution. So a simplified two-dimensional convolution can be represented as this: y sub I comma j is summation over n of k sub m comma n x sub I plus m comma j plus n, where x is the input image, k is the filter kernel, k is the filter or kernel, and y is the resulting feature map. So a filter may correspond strongly to specific patterns such as edges. So modern neural networks learn these filters from data rather than requiring humans to specify every useful visual pattern manually. So modern neural networks learn these filters from data rather than requiring humans to specify every useful visual pattern manually, because it's a lot, right? So it's better the computers learn themselves. So a simple edge detector, for instance, consider the image patch where X is 10, 10, 10, 10, 10, 10, 200, 200, 200. So if you now consider this filter, I think in one of the previous videos we talked about this, that uh how particular filters can some recognize horizontal objects, some recognize vertical objects. So consider this filter. The filter comprises intensity values above the center. So the filter here compares intensity values above and below the center. So negative and positive like that. A strong response indicates a substantial change in intensity, and this is the basic idea behind edge detection. This is how to detect edges. So you can see all these zeros in the middle. We don't care. So it's more about the the top and the bottom. So we want to see what's really happening in those places. So talking about the edge response now. So you want to import number as NP, and you have the matrix X we have there corresponding to the input feature, that's the image patch, and then the filter here. So the response is now so the sum of X K's, if you put all of that together, you can get the filter response. Um, you get filter response 570 like that. So it's more like you have 206 places. That's 1 times 200, 1 times 200, 1 times 200. That's 600 if you add them all up. Then all this minus 10, minus 10, minus 10. That's 600 minus 30. That gives 570 here. So we saw something like this in an earlier video because it's just 10 by 10 multiplication, not the matrix multiplication in that sense. Then we have classification, detection, and segmentation. There are three different computer vision tasks. So we have image classification. The question is, what is this image? And the possible outputs can be, it's a car, it's a lorry, it's a truck, it's this and that. And then that's the image classification. Then we have object detection. So what objects are present and where are they? So a detection can be represented as X, Y, W, H. So X, Y is location, Y W is the width and H is the height. So the model may also produce probability that it is a car, given that we have a particular given a particular image type that it is, right? So, and let's say that probability is 0.97. So it is all probability at the end of the day, but it has to be good enough to avoid accident. So then we have semantic segmentation. The question becomes, which pixels belong to each class? So for every pixel, M sub ij is equal to C, where C is the predicted class. Autonomous driving requires much richer information than ordinary image classification, for sure. And then we have representing a detected car now. Suppose the visual model detects a car with X is 500, Y is 300, the width is 180, the height is 120. So the bounding box can be represented as B, 500, 300, 180, 120, like that. Suppose the model assigns a confidence of the probability that it is a car is 0.96. The model is therefore saying there's a high probability car occupying this region of the image, like that. So however, this still does not tell us the actual distance of the car from the vehicle. That requires geometry now. So you detect the image, but then you also need to know how far away it is. So we have a big problem here. A camera sees only two dimensions. So a conventional camera produces image coordinates UV, but the real world is three-dimensional XYZ. Therefore, autonomous driving AI must infer a mapping between the two dimensions it's seeing and the three-dimension that is the reality. So this is a central computer vision problem. So the most important missing quantity is often the depth. So like, or what you can call the thickness or things like that. So a pixel tells us where an object appears in the image, but not directly how far away it is. So in that case, we need to now talk about camera geometry, talking about the pinhole camera model. So a simplified camera model gives U to be, so U is two dimensions, U are UV. So U is now F times X over Z, and V is F times Y over Z, where X, Y, Z are coordinates in camera space, and UV are image coordinates. So F is then the focal length. So that factors in the idea of length. So the important relationship then is this, that image size is approximately 1 all over the distance. So image size is directly proportional to the distance. So the smaller the image, the bigger the distance. But the bigger the image, the closer, the smaller the distance. As an object moves further away, its image becomes smaller. This relationship allows computer vision systems to estimate depth under appropriate assumptions. So estimating distance now. Imagine a focal length of 800 pixels and actual object height is 1.5 meter. Observed image height is 60 pixels. So using the simplified projection relationship, so H is H over Z, and we solve for Z to be FH over H. FH over H. So F is 800, big H is 1.5, the actual height, and then that over the image height, which is 60. So Z now is equal to 20 when you do all the maths. This is 15 times 80, or even 8 times 15 over 6. So 3 here is 2, 3 here is 5. So uh 2, 5, right? So 5 times 8, 40 over 2. That's 20 meters. So the estimated distance of the image will now be 20 meters. So that way we can do that. So of course we can do a simple Python estimation. So you have focal length in pixels, then you have the observed image height in pixels, and h, the actual object height in meters. So we get the distance in to be 20 meters like we got up here. So we have stereo, geometry, and depth. So when two cameras observe the same object from different viewpoints, the object appears at slightly different horizontal positions. So this difference is called the disparity. So a simplified stereo depth relationship will then be Z equals FB over D, where Z is the depth, F is the focal length, B is baseline between cameras, D is disparity, and then the important relationship becomes Z is inversely proportional to D. The depth is inversely proportional to the disparity. Therefore, large disparity means object is closer, and small disparity means object is farther away. This is one of the fundamental geometric ideas behind depth estimation. So all of this we are doing to actually to see the third dimension of, the camera is seen two-dimensionally. So we need all this now to get the third dimension to the whole thing. So we have example of stereo depth. Now suppose F is 700, B is 0.6 meters, and D is 21 pixels. Then Z is, following the formula, Z is FB over D. So that's F 700 times B 0.6 over D 21. So, and that also ends up giving us 20 meters. This 21 here. 7 here is 100. 7 here is 3. 3 here is 1. 3 here is 0.2. So that's 100 times 0.2. That's 20 meters again. So the estimated depth is approximately 20 meters again. So we can also use a simple Python for code to take care of that. Then we have perspective and vanishing points. Roads contain powerful geometric information, so parallel lines in the real world can appear to converge toward a point in the image called the vanishing point. So a simplified road scene might look like this. So you have two roads running, and then at some point it looks like the roads meet. So the apparent convergence provides information about road direction, camera orientation, lane structure, perspective, and road geometry. So the vanishing point is therefore an important geometric cue for understanding the road. Then we have modeling lane geometry now. So a lane boundary can be approximated by a mathematical curve. A simple model can be maybe the quadratic expression y equals ax squared plus bx plus c. So like a curve like that. So where a, b, and c determine the shape and position of the curve. So the first derivative dy dx is 2ax plus b, and the second derivative d squared y dx squared is 2a. So the second derivative provides a simple measure of curvature in this image space model. For example, if A is equal to 0, the model becomes a straight line. If A is not equal to 0, the model represents a curved lane boundary. So we can talk about lane curvature in that sense. Suppose a lane boundary is modeled by 0.002 x squared plus 0.1 x plus 200. Here, A is 0.02. Therefore, d squared y dx squared is 2a, and d squared y dx squared is 0.004. That's multiply 2 times this now, 0.004. This gives a simple mathematical measure of the curvature of the lane in image coordinates. So we can use the simple Python code to also see that. Then from object detection to object tracking, detecting a car in one image is not enough. So the system needs to know how that car moves over time, right? So because if the car is also moving, all of the speed at which it's going and things like that is very important. So suppose an object is detected at x1, that's 20 meters, and 1 second later it's now detected at 24 meters. So the average velocity can then be computed to be v equals x2 minus x1 over change in time. So that's 24 minus 20 over 1. That's like 4 meters per second. So tracking converts a sequence of observations into information about motion. So it's a lot of cameras doing so many jobs and a lot of calculations going on like that. So for Python, I will just can compute the velocity this way also. Estimated velocity is 4 meters per square second. So in kilometer per hour, we just do the conversion and we get 14.4 kilometer per hour. So that helps also. So you need to, because at the end of the day, every driver is watching their actions relative to other people using the road or other barriers, uh, road limitations and things like that. So talking about acceleration, velocity tells us how quickly position changes. That's what velocity tells us. But acceleration tells us how quickly velocity changes. So the basic equation then is this: A is v2 minus 1 over uh, lambda t over change in t. So suppose v1 is 4 meters per second and v2 after some time, we discover the velocity is 6 meters per second. And after 2 seconds, you discover there's this change in the velocity. Then you see the acceleration is 6 minus 4 over 2, which is 1 meter per squared second. So acceleration is useful because road users do not necessarily maintain constant velocity. So because velocities change, it is important to track the change in velocity. So acceleration gives us that how velocity is changing over time. So, and then we talk about prediction and what happens next. So having all those information, that it's also to help us help the self-driving car to predict what's happening. So once the system estimates position, velocity, and acceleration, it can make a simple future prediction for constant acceleration. So we have x of t plus delta t equals x of t plus v of t delta t plus half is of t delta t squared. So that's classical physics, right? So this is a classical physics equation. So suppose x of t is 30 meters, v of t is 10 meter per second, and then a of t is minus 2 meter per square second. So that's a deceleration now. So that tells you the car is slowing down, right? So change in time is 2 seconds. So you can say x of t plus 2 is 30 plus 10 into 2 plus half into minus 2 times 2 squared. That's 30 plus 20 minus 4, which is 46 meters. Thus, so the at position after 2 seconds, the distance will be 46 meters, like that. So we can do a simple uh a simple Python code to get that here. Now, why is prediction difficult? Real road users do not behave like perfectly predictable physical objects. A pedestrian might continue walking, they can stop abruptly, they can turn, they can cross the road, they can accelerate or change direction. A vehicle might brake, accelerate, turn, change lanes, overtake, or even yield to a driver behind them. Therefore, autonomous driving systems need probabilistic prediction. So instead of predicting one guaranteed future, say the future position at 46 meters, a model can estimate probability distribution. Now, what's the probability that the person will be the future possible behavior will be a particular thing given the current observations. So the goal becomes what are the plausible futures and how likely is each one? Because that way you want to be able to predict what other people or other things around are going to do so that you can fit into the scenario without causing chaos. So we have a multimodal trajectory prediction. Suppose the vehicle approaches an intersection, possible future maneuvers will be left, straight, or right. So a model might estimate, okay, maybe it's going to go left with a probability of 0.15, or it is going to go straight with a probability of 0.70, and right with the probability of 0.15. So this probability sum to 1, as you can see. So the most likely trajectory is straight, but the other possibilities cannot be simply ignored. This is why autonomous driving prediction is fundamentally probabilistic. So representing an object state now, a vehicle does not need to represent an object only by its image location. So a simplified state vector might be x of t, y sub t, v sub x comma t. So that's velocity in time and at a position x in time, and v also. So this represents position in x, position in y, velocity in x, and velocity in y. And this can now be used to calculate the acceleration like we saw before. So a richer representation could include s sub t equals x sub t, y sub t, z sub t, v sub x sub t. So more information that can really help. So we have z of t talking about acceleration, theta of t talking about orientation, c sub t talking about object class. So the AI is therefore constructing an evolving numerical representation of the world. So it's like it's constantly rerouting. So it's more like we can think about Google Map, right? You have GPS, helping you to locate. And when you go a particular way, so rerouting occurs. But in the case of autonomous driving car, so the rerouting is occurring. I mean, the information update is happening so much faster because it's a more serious situation, right? So you are looking at other vehicles, other people, the barriers and everything relative to your own position and your speed and all that. Then we talk about the state space modeling. A simple constant velocity model can be written as s sub t plus 1 equals a s sub t plus w sub t, where w sub t represent process uncertainty. So there's a level of uncertainty we have there. So for a one-dimensional motion, s sub t is xt vt, and a can then be 1 change in time, then 0 1. Therefore, x sub t plus 1, v sub t plus 1. That's location, right? That's position and velocity. That would now be one lambda t zero one x tvt. So this is the mathematical foundation of simple motion prediction and state tracking. So this for the state space model at any point in time. So we have so state prediction now. So you have an array like this, and then you have so let's say change in time is 2 seconds. So maybe every 2 seconds you have this going, and then on the current state is 25. That's talking about the state and the velocity. And yeah, and then the next state can be predicted by just multiplying the matrix A by the current state, and then you can predict that, oh, the next state, the location is going to be 30 and the velocity will be 5, like that. So that's what we have there to predict the state. That's the location, the position and velocity. So talking about coordinate systems now, autonomous driving systems must transform information between different coordinate systems. Image coordinates, you have UV, camera coordinates, X, C, Y, C, C, Z, C. Vehicle coordinates, you have XV, YV, ZV. World coordinates now, you have XW, YW, ZW. So you have many things running together. So a point detected in an image must eventually be interpreted relative to the vehicle and the surrounding environment. So this requires coordinate transformations. So you have ideas about rotation and translation. So a rigid transformation between coordinate systems can be written as P prime equals RP plus T, where R is a rotation matrix and T is a translation vector. So you have rotation and translation happening concurrently. So using homogeneous coordinates, you can have X prime, Y prime, Z prime 1, then that's equal to RT. So the R now rotation matrix, you have translation vector 0, 1 multiplied by XYZ in the current state, XYZ 1. So this mathematical operation allows the system to relate observations from cameras to the vehicle's coordinate system and ultimately to a representation of the surrounding world. So, why vision, geometry, and prediction must work together? Suppose computer vision detects there's a pedestrian. That is only the beginning. The vehicle also needs to estimate where is the pedestrian, how far away is the pedestrian, how fast is the pedestrian moving, which direction is the pedestrian moving, what trajectory is plausible, could that trajectory intersect the vehicle's path? Therefore, so vision identifies plus the geometry locates, tracking estimates motion, and prediction forecast. So this is the central mathematical structure of the lesson. So vision for identification, geometry for location, tracking for estimating motion, and prediction can tell what exactly is going to happen next. And then the car itself now behaves according to the information. Then we have collision prediction. So collision is a big deal when it comes to driving any kind of vehicle, even cycling. So you don't want to hit people on the road. You don't want to hit other bikers. Or if you are driving, even if as a human driver, you don't want to run into anything. So we need to be able to predict collision. So suppose the vehicle follows trajectory T sub V of T, and another road user follows T sub 0 of T. A simplified collision risk condition can be the absolute distance between TV of T minus T0 of T less than D safe. So where D safe is the safety threshold. So once it is less than the safety threshold, the car will have to stop. So I mean, in normal driving, right, there's a distance you should maintain between the vehicles in front of you and all of that, right? So the distance is therefore comparing predicted future trajectories. So this is more sophisticated than simply asking, is another vehicle nearby? The important question is, will our predicted paths come dangerously close in the future? So you want to give the necessary space for other vehicles to avoid any collision risk. Let's take an example of collision risk. Suppose that after 2 seconds, TV of 2, you have 30 meters and T naught of 2 is 31 meters. Suppose the safety threshold is 2 meters. So the predicted separation is actually seen to be 1 meter, and since one is less than two, so the safety threshold is 2 meters. The predicted separation is below the simplified safety threshold. So therefore, this scenario should be classified as a potential collision risk. So you don't want to be in that situation where you are below the safety threshold. So here we can then have a kind of collision collision check. Vehicle position is 30, object position is 31, safe distance is 2. So if you calculate the absolute value between the vehicle position and object distance, you get 1. So if distance is less than safe distance, you print potential collision risk. Else, print no immediate predicted collision. So if you run this now, you get a potential collision risk. So if say the distance between uh the vehicle position is 30 and object position is actually 32. So there's no immediate predicted collision in that case. So, but if you have even like 1.5, yeah, even 1.4, there's going to be a risk. Oh, this still no immediate collision risk. Okay, that should be less than the safe distance. So it's still less than the safe distance. So the safe distance itself is 2. So, okay, yeah, this is what I changed. So the safe distance is 2, right? And if this is 31, let's even say if it is 30. So potential risk of collision. In fact, that's too close for comfort like that. So potential collision risk. Then time to collision now. So if there's a collision risk, we also want to compute how much time will it take for the collision to take place. Another useful quantity is TTC, that's time to collision. In a simplified one-dimensional situation, TTC is the distance over the V closing. So D, that's the current separation over the closing speed. So suppose D is 30, the current separation is 30 meters, and the closing speed is 10 meters per second. Then the TTC is 30 over 10, which is 3 seconds. So this is simplified educational calculation. It doesn't mean that that's the reality in every Tesla vehicle you see. No, this is just an idea of what is really happening, because in reality, things are more serious than what we have here. So this is just like a simplified educational calculation here. So real collision prediction must account for multidimensional trajectories, acceleration, uncertainty, road geometry, and many other factors. So, of course, we do a simple Python code for this. Distance is 30, closing speed is 10. Then the time to collision will be 3 seconds as computed there. Now, why video is more informative than a single image? Now, a single image tells the system something about the current scene. A sequence of images tells the system how the scene is changing. Suppose we have frame 1 is this, frame 2 is this, frame 3 is that. So you can see an increasing distance. Now, if you take a reference from here, so from here to here, this is the distance. From here to here, it increases a bit. From here to here, it also increases further. So from one frame, we can estimate position. From multiple frames, we can estimate the direction, the velocity, the acceleration, the object behavior, the relative motion. So a temporal model can therefore be represented conceptually as Z sub t equals f of I sub t minus k all the way down to I sub t minus 1, then comma I sub t, where Z sub t is a learned representation of the current temporal context. Then we have optical flow. Optical flow estimates apparent pixel motion between consecutive images. So if a point moves from x1 comma y1 to x2 comma y2, then the displacement will be u, which is x2 minus x1, and the velocity will be y2 minus y1. So I mean, u is this, v is that. So the motion velocity, the motion vector, then d is uv. So optical flow is a classical computer vision concept that helps illustrate how motion can be inferred from image sequences. So imagine that we have x1, y1 to be 100, 200, x2, y2 is 108, 208, 203. So u now is x2 minus x1, that's 108 minus 100, which is 8. And then v is 203 minus 200, that's 3. So if you print, the horizontal displacement is 8, vertical displacement is 3. So we have that right there. And then we can also talk about depth from motion. So, of course, for an autonomous vehicle, so there might be motion involved between on it and other vehicles, right? So movement of the vehicle creates additional visual information. Suppose the vehicle approaches a stationary object. As the distance decreases, z decreases like that. So the apparent image, the apparent image size generally increases. So as you get closer, image increases. So this relationship provides information about depth. Therefore, a sequence of images can contain information about both appearance and motion. So modern learned vision systems can exploit temporal patterns to infer scene structure and motion. Then we have neural networks learn scene representations, right? A neural network can transform an image into a learned representation, I1 to Z, where Z is a latent representation. That representation can then support multiple tasks. So, like object detection, depth estimation, segmentation, lane estimation, motion estimation, and trajectory prediction. The important concept is representation learning. So it's all about representation. And you want to get the representations right to avoid trouble. So instead of manually programming every visual rule, the model can learn useful patterns from large amounts of training data. So it's all about the data, right? So once the data is in place, the and whatever model is being used can Tesla AI, for instance, can actually learn what it needs to learn from the available data. And that's why data is more important than that. Data is really important in this case. So training the model, now suppose the model predicts y cap while the true value is y. So for a regression model, a basic loss function is measured, is mean squared error, right? So LMSE is 1 over n. We've seen this a lot. Then for classification, you can have cross entropy, which is commonly used like summation over C of YC log PC. So this is for cross entropy when you're classifying. This is for regression. Then a complex perception, a complex perception system, we optimize several objectives like L, you have lambda 1 times the detection, lambda 2 talking about depth, lambda 3 with L segmentation, lambda 4 L prediction, and all that, where the lambda values determine the relative contribution of each objective. I think we saw the same kind of thing when we talked about prediction systems for Netflix and all of that. So example now, we have suppose if the true future positions are 10, 20, and 30, while the predicted positions are 12, 18, and 31. They're pretty close, but there are still errors. So the errors are uh, 10 minus 12 minus 2, 20 minus 18, 2, 30 minus 31 minus 1. So the squared errors are 2 minus 2 squared 4, 2 squared is 4, minus 1 squared is 1. Therefore, MSE is 4 plus 4 plus 1 over 3. So the mean squared error is actually 9 over 3, which is 3. So the model's mean squared prediction error is 3. So, and of course, we can also do that here and we get the same 3. So uncertainty is fundamental in this whole self-driving car system, like Tesla, like what you have for Tesla AI. So um, no perception no perception system is perfectly accurate, none. So a model might estimate probability of pedestrian given the image is 0.92 rather than p equals 1, so no guarantee. A depth estimate might be z equals 25 plus or minus 2 meters. So it gives margins of error. So a velocity estimate might be v equals 8 plus or minus 1 meter per second, and future behavior is even more uncertain. Therefore, autonomous driving AI must reason under uncertainty. So the important question is not simply what is the answer, but what is the best estimate and how uncertain is that estimate? So you can have allowance, you can factor in possible errors for maximum secure safety. So many autonomous driving simulation, we can combine several ideas into a small simulation. Suppose an object is 30 meters away, moving at 10 meters per second, and accelerating at minus 2 meters per second. That's it's basically slowing down. So we want to estimate its position 2 seconds later and calculate a simplified time to collision. So the two calculations demonstrate the distinction between future position prediction and collision timing estimation. So here you have end-to-end mini simulation. Import number as NP. So you have current state, distance 30, velocity 10, acceleration minus 2, and then prediction horizon is 2.0. So future position using constant acceleration physics now. So future distance is distance plus velocity times change in time plus 0.5 times acceleration times dt squared. Then simplified time to collision will now be distance over velocity like this. And then we run this and get the values. So predicted distance after 2 seconds is 46 meters, and current simplified time to collision is 3 seconds. So the complete mathematical pipeline we then have here is this. We can summarize the entire lesson using the following conceptual sequence: I of t to f of t. That's camera image at time t. So then taking the visual features, then the detected objects, the geometric scene representation, the current scene state, and then you have the predicted future states, and then you have selected vehicle action. So at the end of the day, taking all this into consideration, you take an action. Either do you slow down, do you speed up, do you stop altogether, or do you start moving again? So in plain language, you see, so the autonomous vehicle sees, understands, locates, tracks, and predicts, and then makes and acts. So why this is AI mathematics? Autonomous driving provides an excellent example of how several mathematical disciplines combine inside an AI system. So that's what the thing we have seen from the beginning. So any kind of AI system you're talking about, like natural language processing, machine learning, now computer vision, recommender systems like or even expert systems or even robotics. It's all about different kinds of mathematics coming together, and it's usually involving linear algebra, probability statistics, and all these things. So why this is AI mathematics? Autonomous driving provides an excellent example of how several mathematical disciplines combine inside an AI system. So linear algebra is used for vectors, matrices, coordinate transformations, neural network operations. So like y equals ax, that's very fundamental to a linear combination like that. Then you have geometry. So this is used for camera projection. So first we start with linear algebra, right? Then you have geometry. This is used for camera projection, depth, perspective, lane geometry, and 3D reconstruction. So a popular formula there is U equals F times x over z, where f is the focal length, like that. Then you have calculus, of course, always there, which is used for velocity, acceleration, curvature, and optimization. As you can see, the velocity and acceleration computed from the location, the displacement. Then probability, which is used for uncertainty, object classification, and trajectory prediction. So there you want to see what's the probability of future actions given current observed patterns. Then you have optimization there, which is always there. So at the end of the day, so as all of these things are playing out, optimization helps you to minimize the loss or the difference between predicted value and the actual value. So this is used, optimization is used to train neural networks. So you have theta star equals the minimum loss over the whole parameters available. So autonomous driving AI is therefore a powerful example of applied mathematics in the real world. So the key takeaways we have here as follows. The most important ideas from this lesson are: a camera produces numerical pixel data, not semantic understanding. So just like a machine, and AI does not understand your text or words in human word, human text, or even images, you know. So they only understand anything you put as a human. The AI has to break it down to understand and then give you back what you understand. So computer vision transforms pixels into useful representation of objects, lanes, and other scene elements. An object detection that identifies both what is present and where it appears in an image. Then camera geometry helps transform 2D images measurements into estimates of 3D position. So a simplified pinhole camera model gives U equals Fx over Z, and stereogeometry can estimate depth using Z equals FB over D. So tracking multiple frames allows the system to estimate velocity and acceleration. So future position can be approximated using this formula: x of t plus change in t equals x of t plus v of t times change in t plus half a of t change in t all squared. So real world behavior is uncertain, so prediction is naturally probabilistic. So you usually have a probability of y given x. So probability of future behaviors given what is currently happening. So collision prediction compares future trajectories rather than simply detecting nearby objects. So the big idea is you have computer vision plus geometry plus motion plus probability plus prediction, leading to machine understanding of the road. So the final challenge now, we want to try this out. Imagine a camera detects a pedestrian who is 25 meters ahead. The system estimates V to be velocity to be 2 meters per second toward the road. Then at the same time, the vehicle is moving toward the pedestrian at 8 meters per second. So ask yourself, what information comes directly from computer vision? What information requires geometry? How can consecutive frames estimate the pedestrian's velocity? What additional information is required to predict the pedestrian's future trajectory? How could time to collision be estimated? Why would a probabilistic prediction be better than assuming one guaranteed trajectory? This illustrates the central lesson. Understanding the road means predicting the future of a changing three-dimensional world. So that leads us to our practice problems, where I get to solve two of the problems usually. So, in this case, I'm going to solve problems 6 and 14. So here you can see all of problems 1 to 9. You can see everything from 1 to, or even, okay, you can see everything from 1 to 9 here. So I'll be solving 6. 6 says a stereo camera system has focal length f is 800 pixels and baseline b 0.5 meters. An object has disparity d 40 pixels. Estimate its depth. So I'll be taking care of that. So the next problem to solve will be 14. So you can see 1 to 9 here. Then here you can see 10 to, you can see all of 10 to 18. So the next problem I'll be solving is 14. A vehicle has position x 50 meters, velocity v 12 meters per second, and acceleration a is minus 3 meters per square second. Predict its position and velocity after 4 seconds. So I'll be taking care of that also. And then you have the rest of the problems. So let's quickly go on to take care of the problems. So problem 6. A stereo camera system has f to be 800 pixels, then b is 0.5 meter, and the disparity d is 40 pixels. And we know that the stereo depth equation is z equals fb over d. So substituting values. So z now can be said to be 800. F is 800, right? B is 0.5 and D is 40. So if we put all of that together, this is 400 over 40. That means the hmm, Z is equal to 10 meters. That's the stereo depth right there. So the object is approximately 10 meters from the camera. So we can say so the object is approximately 10 meters from the camera. Okay, with that out of the way then, let's go for problem 14. Problem 14. So a vehicle has x is 50 meter, velocity 12 meter per second, acceleration minus 3 meter per squared second, and change in time because we are interested in what happens after 4 seconds. So change in time is 4 seconds. So we have all of this. So first, we need to calculate the future velocity. Calculate the future velocity after 4 seconds. So v future is equal to v plus a times change in time. So that's equal to, so v future then is equal to, the velocity we have is 12 meter per second. So that's 12 meter per second. Acceleration is minus 3. Change in time is 4. So that means we have v future to be 12 minus 12, which is 0 meter per second. So it means the vehicle is slowing down, right? So being able to calculate that will actually give the signal that you have to stop at some point. So now we calculate. So if it stops like that, now we need to calculate the future position. Where is it going to stop? That's important. Now calculate the future position. The future position. So we have x future equals x plus v change in time plus half a change in time all squared. So, and what that tells us is this now, that x future is equal to, so the initial x, right, we know is 50 meters. So we have 50 plus the velocity 12, change in time is 4, plus half, acceleration is minus 3, then this is 4 squared. Change in time is 4 squared. So we have 50 plus 48 Then this is 16. 4 squared is 16, right? 16 divided by 2, 8. 8 times minus 3, that's minus 24. And if that is the case, that means that so that means that x future then is equal to 50 minus 40, that's 98. 98 minus 24, that's 74 meters. So that would be the future position. So to now be 74 meters away. So so now we have x future 74 meters and v future is 0 meter per second. So in this case now, we can now see that under under constant acceleration assumption, under constant acceleration assumption, the vehicle reaches 74 meters after 4 seconds. After 4 seconds, and its velocity becomes 0 at that instant. So, and this gives us a glimpse into how Tesla AI sees what's happening on the road, how Tesla AI understands what's happening on the road, how Tesla AI understands the road. Yeah. So we have that. Again, I'm going to flash the questions and then it will be done. So here you can see questions 1 to 10, all of question 1 to 10 right here. I did 6. I did question 6. Then you can see questions 11 to, okay, let me see. 11 to 20 should be possible, is it? Yeah, it is. So you can see all of 11 to 20, where I also did question 14. Yeah, I did question 14. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, this is a good time to go ahead and subscribe as well. You can hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of the channel also by clicking on join. That gives some special privileges when you that you see when you click on join. Ultimately, don't forget to comment, like, and share so that other people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.